Okay, we're going to look at Galois groups of a little bit more complicated extensions where we add many roots. And so what we're looking for automorphisms sigma from Q adjoin root 2, root 3, root 5 to Q adjoin root 2, root 3, root 5. And let me actually call it alpha to just be consistent, or rho actually, be consistent with the book's example here. All right, so we're looking for automorphisms here. They automatically are going to fix Q pointwise, so we don't need to consider that. Now, by what we've done before, we know that any such function rho, any automorphism rho, must send root 2 to a square root of 2. There's 2 of them. Root 3 to a square root of 3. There's 2 of them. Root 5 to a square root of 5. And there are 2 of them. And in fact, there will be an automorphism for each one of these, and then also all their composites. So this is going to be kind of wild. Now, let's make an observation here. We can check that t squared minus 5 is irreducible. It's clearly irreducible over Q, but it's also actually irreducible over Q adjoin root 2, root 3. And t squared minus 3 is irreducible over Q adjoin root 2, root 5. And t squared minus 2 is irreducible over Q adjoin root 3, root 5. And so since it's irreducible, there exists automorphisms rho 5 from root 2, root 3, root 5. Rho 5 is, the subscript is just telling us what's going to happen. Okay, that you can use whatever notation you like, but I like the subscript. I'm going to follow book's notation subscript with what it's going to do. So there exists an automorphism over Q that fixes Q adjoin root 2, root 3 that interchanges the roots. There exists an, I'm going to say there exists autos rho 5 with rho 5 of root 5 is negative root 5. There exists an automorphism. In fact, let me write it like this a little bit better. There exists automorphisms rho 2, rho 3, rho 5 such that rho 5 of root 5 is negative root 5 and it fixes the other two. Because it's we're using this fact that if you have an irreducible polynomial, there exists an isomorphism between extensions where you add in the separate roots, but when we add in root 5 and negative root 5, we get the same thing. That's something we saw in the previous video. And rho 3 that sends root 3 to negative root 3 and fixes the other two. It's probably a better way of presenting this, but this is the way I've chosen. And rho 2 that negates root 2 and then fixes the other two. Okay, so these are 3 separate automorphisms. And turns out when you compose them, what's going to happen? Well, if I negate root 5 and then I negate root 3, and when I first negate root 5, I fix root 3, and then when I negate root 3, I fix root 5, that's going to be the same as first doing rho 3 and then doing rho 5. Okay? So I don't know why I put the braces here. So it turns out that these actually commute. So when you negate one and then negate the other, that's the same as negating the other and then negating the first one. And they square to the identity. Okay, so they commute and they square to the identity. So they generate a group isomorphic to Z mod 2 cross Z mod 2 cross Z mod 2. And the isomorphism is pretty simple. If we, I know that group theory has happened a while ago. If we think of Z mod 2 in the standard way, 0, 1, then any element of the group generated by these guys is going to be some power of some composite of these guys. So that power is 0 or 1, because when we square them, we get the identity. So it will never pass 0 or 1. And we're going to send that to ijk. So for example, row 2 is going to go to 1, 0, 0. Let me give myself a little more space here. Row 3 is going to go to 0, 1, 0. And row 5 will go to 0, 0, 1. Okay, so that's what it does to the generators. So one can readily verify this is an isomorphism. Furthermore, any automorphism can only send the roots, root 2, root 3, root 5, to plus or minus themselves by the standard arguments we've been doing, right? Root 2 must go to a square root of 2. Root 3 must go to a square root of 3, and so on. And so any automorphism you can build, because, if you need to negate both root 5 and root 3, you do row 3, row 5. If you need to negate all of them, you do row 2, row 3, row 5, and so on. So any way of negating the roots you can build with these generators. So the Galois group of Q adjoin root 2, root 3, root 5 is actually just these guys. It's it's the group generated by row 2, row 3, row 5, and that's abstractly isomorphic to Z2 cross, I'm going to write it like this, Z2 cubed. Oops, cubed. If we wanted to write out all the elements, we get the identity. We get row 2, row 3, row 5. We get row 2, row 3. We get row 2, row 5. We get row 3, row 5. And we get row 2, row 3, row 5. So there's 8 elements there. 1, 2, 3, 4, 5, 6. Yeah, there's 8 elements there. And that is the Galois group of this more complicated extension. And let me notice something real quick before we end our examples with this video. The extension Q adjoin root 2, root 3, root 5 has degree 8. And there are 8 elements here. I've listed all of them. Notice also that the elements here, they have all of their conjugates. So root 2 is an element here, excuse me, and it has negative root 2 is in this field. Root 3 is an element here, it has negative root 3. Root 5 is an element here, negative root 5 is there. So it has sort of all the possible roots that you'd want if you just cared about root 2, root 3, root 5. That is square roots of 2, 3, and 5. And the degree of the extension is the same as the order of the Galois group. Now let's contrast that to the example we did previously, where we did, let's see, the cube root of 2. The degree of this extension, you put it as a note on the side here, the degree of Q adjoin C over Q is 3, of course, right? Because we add in a cube root. However, the order of the Galois group is 1. It's not 3. What is different here? Well, we didn't have access to all the roots that we needed if we added in a cube root of 2. We only had access to one of them. And so there's a discrepancy here. The order of the Galois group is less than the degree of the extension. And we're going to find out it's always less than or equal to. And it's equal to provided you always have access to the roots you need. And there's another example. In this guy here, we found that there is, let's see, how many did we found there's 2 elements of the Galois group, right? So the Galois group has size 2, whereas the degree, let's put a thought bubble here, the degree of the extension where I add in a 4th root of 2 is 4. 2 is not equal to 4, certainly, and the problem is we were missing access to the other 4th roots of 2. We had access to 2 of them, but not all 4, and that caused a discrepancy between the degree of the extension and the order of the Galois group. And so we're going to care mostly about we're going to care about all extensions, but the fundamental theorem is only going to apply to these special types. And these are, we'll get to, I believe in the next chapter, are called splitting fields. So the fundamental theorem of Galois theory will apply to these splitting fields.